Hello everyone, welcome to the course Material Characterization. This is the live problem solving session for the week 12 of the course. I am Mayan Goyal. I am a research scholar at the Department of Electrical Engineering, IIT Bombay. This course is being taught by Professor S. Shankaran, who is an associate professor at the Department of Metallurgical and Material Engineering, IIT Madras. The course plan for week 12 is sample preparation and applications of TM and instrument details and demo experiments of TM. This session has been happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So like previous weeks, I will be showing you an overview of this week's topics using AI generated slides. So, so TM column consists of four zones. First is generation, where your cathode assembly and your node sits where your beam is generated. Second is illumination, which contains your condenser lenses, which converge and shape the beam. Next is your interaction, where your specimen stage and objective lens sit. And last is projection, where your intermediate lenses, diffraction lenses, and the fluorescent screen or CCD camera sits. So first is a beam generator generation. Uh, So the beam is generated through a cathode, which could be tungsten or lanthanum hexaboride, and the beam is generated through electrons are generated through thermionic emission, and then they go towards a positively charged anode is used to accelerate the electrons to the required energy. So you can see here we are talking about two different models here. One has an accelerating voltage of 120 kilovolts. Another has 200 kilovolts. So the 200 kilovolts will have a shorter wavelength. That means it has a higher resolution, and that is why it can be used for more finer to view finer things. Also, the primary purpose of the 120 kilovolt TM would be to see high level morphology and lattice structures, whereas for the 200 kilovolt we will go for to see atomic resolution and fine lattice fringes. Now, so we know the electromagnetic lenses generate massive heat with up to 120 degrees Celsius. So a thermal shield which consists of constantly chilled, which consists of constant circulation of chilled water to maintain the temperatures and keep it in the operational range. And then we have inside the column we have ultra high vacuum there. So the ultra high vacuum generation requires the three different pumps. So first is your rotary pump, which will bring the vacuum from room ambient vacuum to up to like -3 torrs or -3 millibars. Then there would be an oil diffusion pump, which will bring it down to like minus 6 millibars. Then there will be a getter ion pump, which will then further bring it down to minus 12, 9 or minus 12 millibars. So next would be the bending and clipping. So we use electromagnetic lenses in the condenser. So so that will sharpen, converge or diverge the beam, manipulating the beam using magnetic fields. And after that, there will be mechanical apertures which will be used to shape the beam. So condenser aperture reduces physical beam diameter, whereas if objective apertures are used to alter image contrast by physically blocking scattered electrons. So both have different purposes. So next we have our specimen. So the core rule is a specimen must not exceed 100 to 150 nanometer in thickness, because thicker materials will completely absorb the electron beam and there won't be any transmitted beam. So due to that, to we have to thin down the material. So let's say if you have macroscopic materials like metal here, so they are thinned by electrolysis method. If you have materials like rocks, they are thinned down using a non-conductive method such as ion milling. Or if you have powder, then they are dispersed directly onto carbon coated copper grids. So the mesh provides physical shadow and structural support. So we dilute the powder and disperse it onto a very fine copper grid, which provides structural support to our very fine powder, thin and fine powder, as well as it can be used to as a shadow to bring contrast. Then the beam specimen interaction, we have characteristic characteristic X-rays. So first we'll have transmitted electrons which pass directly through less dense or perfectly aligned areas. Then we'll have scattered electrons in all directions which bounce off at exact angles that specify the Bragg's direction, so which is electron diffraction. And then there will be characteristic X-rays, which is energy released by specific elemental atoms upon impact. So which would be your K alpha, K beta, L alpha, etc. X-rays. Then the imaging is done by in bright field and dark field. So in bright field mode, you the aperture selects the transmitted beam and the dense diffracting areas are block electrons and appear darker, whereas thinner areas appear brighter. And this contrast is used for imaging. And in dark field mode, the aperture selects one specific scattered beam and only areas corresponding to the that exact crystallographic plane will light up and everything else will be dark. So the image formation is done by projection via intermediate and diffraction lenses onto the fluorescent screen. So you can see in the image it is of carbon nanotube powder which is dispersed on a carbon coated copper mesh grid. And so at 200 kilovolts, the magnification reaches 5 nanometer scale, which is able to resolve literal lattice fringes, which you can see here. We are able to see spacing between carbon planes of 0.34 nanometers. Next can be done with, apart from imaging, we can do crystallography and diffraction. So we do selected area diffraction. So for that we insert the SAD aperture, which isolates a specific region to determine exact lattice orientation. And then we can use fast Fourier transform, which so digital processing allows us to convert lattice images into diffraction patterns, which allows measurement of sub-nanometer spacing, such that resolving 2 nanometer spacing in two-phase alloys. Then we can do chemical identification using EDX. So energy dispersive X-ray analysis captures characteristic X-rays to yield both qualitative identification and quantitative atomic weight percentages directly from the nanoscale target. So, so the characteristic X-rays are captured using a silicon or lithium detector, which is cooled via liquid nitrogen to have to have very less noise. And then using characteristic X-rays, it can create a spectrum of all the elements that are present and their atomic or weight percentages inside the material. So that is what everything that is happening inside the TM. But outside you have the controls, which are, you can have beam alignment and intensity control. So you can change the kilovoltage, the heating temperature of the filament, intensity knobs like convergence, divergence using condenser lenses and aperture, as well as stigmatures improve to improve the resolution, reduce stigmation and other errors. Then you have navigation, which is precise XY translation and XY translation of your sample. Use centric focus and wobbler knobs to maintain optical axis during tilt. Next, we have image capture. So for that, you can do coarse and fine focus. You can change the magnification. You can toggle between dark field, bright field, as well as you can change the spot size. So you can do morphology, crystallography, as well as chemistry all together. So the ultimate goal of TM is to characterize the material in its original pristine state, but we need to prepare a sample that requires systematically destroying. So the sample preparation requires systematically destroying it to create an infinitesimally thin section, which is transparent to electron. So we have two mandates. So one is the material should be thin, that is, electron must be able to transmit through the material, as well as pristine. The process must not introduce external strays, structural defects, or chemical contamination during the thinning. And so preparation can take anywhere from 10 minutes to 2 days, depending on the material and required insights. So there are two. two techniques. One is pre-thinning and one is final thinning. So for metals and alloys, pre-thinning is done using uh, creating a 3 disc punch, and then final thinning is done by electropolishing using twin jet. For ceramics and non-metals, pre pre-thinning is done by ultrasonic cutting and dimpling, and final thinning is done by ion beam milling. For soft polymer and biological samples, pre-thinning is done using ultramicrotomy, that is diamond knife, and final thinning is also done using ultramicrotomy but directly at the grid level. Then for second phase particles, pre-thinning is done by replication and carbon coating, and final thinning is done by chemically extracting the material. And there's a standard of the material radius around of having the material radius around 3 millimeters. So the most solid samples must eventually fit within a standard 3 millimeter TM grid or a self-supporting disc. So how the materials get damaged during thinning? So abrasive papers used for initial mechanical thinning inherently introduce surface damage, that is strain dislocations that mask the material's true characteristics. So you can see the thickness has to be around 6 times the grid size because the damage depth is itself three times the grid size. So that should be able to leave the pristine material of about 3 times the grid size. So finer samples demand finer emery paper. Using coarse abrasives on thin samples permanently embeds mechanical damage into the finer team specimen. Then we have to also take using while using chemicals, we have to take care of chemical hazards. So common laboratory agents like HCl, HF, HNO3 and HClO4 are highly poisonous and potentially explosive. So preparation is a strict recipe, and deviating from the recommended density line shifts the mixture from a safe electrolyte to an explosive hazard. So the universally polished that is used as a mixture of perchloric acid, which is HClO4, with plus ethanol or methanol. It is capable of polishing most metals, but requires strict adherence to safe density lines on the phase diagram. So if you shift to even slightly, you can create an explosive material or a flammable material. So then pre-thinning. So that is preparing the 3 millimeter canvas. So for ductile things like metals and alloys, we use mechanical disc punch, which is it creates a 3 millimeter disc, cuts out a 3 millimeter disc from your thin sheet. So it ejects 3 millimeter disc diameter self-supporting disc from thin ductile sheets. Whereas for brittle materials like ceramics and non-metals, we use dimpling. So it uses a grinding wheel and abrasive slurry to mechanically carve a concave dimple into the center of an ultrasonically cut 3 millimeter ceramic disc. So it incorporates a light pipe and mirror system to visually detect the exact moment of perforation. So an abrasive grinding tool and abrasive slurry is used to ultrasonically cut out a 3 millimeter dimple in the sample, which is used to separate from the sample. Then final thinning is done using polishing. So electropolishing is strictly for electrically conducting materials. It leaves no mechanical damage, but surface chemistry can change. So there's a Goldilocks IV curve for electropolishing. So if your voltage is too low, then it will result in etching, and if your voltage is too high, then it will result in pitting. So you need to keep the voltage and current appropriate in the polishing zone. So the target state is a stable viscous fluid film and a thin solid oxide layer that forms between the electrolyte and the specimen surface, which protects it from etching or pitting. So what a twin jet polisher does it, the specimen, which is a positively charged 3 mm disc, is held vertically, and then the jets, which are dual nozzle pumps, which recirculate cooled electrolyte through a liquid nitrogen bar directly onto the center of both discs, both sides. And then there's a sensor, which is a light pipe which detects a precise millisecond a microscopic hole is perforated and triggers an alarm to stop the polishing further to prevent damage. So the rule of thumb is success requires trial and error. You must systematically balance temperature, solution chemistry, stirring rate, and applied voltage. So yeah, you may have to do it multiple times and you have to keep record for each time so that you can improve your method. So the critical window for post polish protocol. So before polishing, inspect the sample under an optical microscope. Residual glue or emery debris can cause uneven thinning, so you have to first clean it. So the moment the light sensor beeps, you have to extract the sample instantly because and clean it. So because the residual electrolyte will cling to the surface and actively continue etching it. So you have to do 3 beaker wash. So do not use 1 beaker, which vigorously agitate the sample through 3 successive alcohol baths to completely halt the invisible chemical etching. Failure here will ruins the sample. for for non-conducting samples, we use ion beam thinning. So where we focus a very fine argon ion beam on our sample to physically etch it. So we shoot an argon gas, create ion. Then in the ionization chamber, we create the ion plasma, and then we shoot a very fine focused beam on our rotating sample, and the beam can be up to 6 kilo electron volts of energy. So unlike chemical electropolishing, bombarding a sample with argon ions physically damages the surface. incorrect parameters will lead researchers to characterize ion-induced prone characteristics, that is, ion-induced defects, rather than the material's actual nanostructure. So you can see here the same cadmium tellurium specimen. When it was thinned by reactive iodine, it is pristine, undamaged. But when it was thinned by argon ion beam, it defects have been created. Then we use a method cross-sectional preparation, where we first slice the bulk sample into extremely thin perpendicular according to our interface of interest. Then we sandwich the slices with alternating with spacer layers, which could be silicon or glass, and they are wider than the grid slot. Then we mount the assembled club sandwich into an open slot in a TM grip and secure it. And then we mill the uh, assembly assembled grid is milled in an iron beam miller till perforation occurs at the interface. Then for soft materials, ultra microtomy is used. So the mechanism is a thermally advanced mobile arm is feeded for polymer or epoxy embedded sample block against a fixed cutting edge. So have a fixed edge of diamond or glass knife, and you use a precise mobile arm to cut to place a polymer or your sample block on it to cut it. And then there's a TM grid floating in the so there's a bath which is called a trough. So the ultra thin flakes are shaved off and slide directly into the fluid filled trough, and they keep floating on the surface using surface tension because of surface tension. And the TM grid is then collect, inserted in the trough, and the floating inert sections are gently phased out using a bare TM copper grid, which are ready for immediate observation. So for second phase particles, we use carbon extraction. So let's say we have particles embedded in a material. So like in magnetic samples like steel, the bulk metal matrix interferes with the electron beam. And if you want to characterize second phase particles, they must be completely extracted from the host. So first we do etching to open up the second phase particles. Then we coat it with a carbon film, and take then we remove the carbon film, and the second phase particles come along with the carbon film. So regardless of the arduous preparation part taken, every specimen arrives at the final gate at uh, uh, is highly corrosive and susceptible. Most electron beam contamination originates from the sample itself and not a dirty vacuum. So the final step is plasma cleaning. So that is bombarding the surface with energetic electrons and ions of argon, oxygen, nitrogen for a short duration like 3-4 minutes. And what it does it breaks carbon hydrogen bonds and reduces hydrocarbon molecular weight. So they are then pumped away, and it leaves the actual specimen surface completely unaffected and perfectly pristine for the TM. So to yield functional bright field, dark field, or high resolution lattice images in a TM, the sample must allow an electric beam to pass completely through it. So we need a terminal thickness of less than 100 nanometers without destroying the material's underlying microstructure. So first we use initial shaping, which is a disc cutter or a disc punch. Then we use dimple grinder for thinning, and then for iron beam milling for final. So we just said that for metallic samples we use electrolytic polishing, but in some cases metallic samples require iron milling because electrolytic polishing can cause second phase particles to prematurely fall out of the alloy matrix. So the ultrasonic disc cutter is a specialized tool for rapidly extracting 3 mm discs from hard ceramic slices. So it is a tubular tube, and it gives ultrasonic vibrations in kilohertz, and there is an abrasive slurry. So piezoelectric crystal generates ultrasonic vibration at 26 kilohertz, and then an abrasive chemical ceramic slurry such as boron carbide, nitride, or silicon carbide is used as a cutting mechanism. So the vibrating tubular tool derives the slurry into the substrate, achieving rapid localized erosion without shattering the brittle ceramic. Then we use dimple grinders. So before iron milling, ceramics and metals must be pre-thinned. A rotating grinding wheel uses ceramic slurry to carve a microscopic dimple into the center of the 3 mm disc. So you mount the sample into an aluminum stub using specialized glue. Then your grinding wheel rotates over at the center, and it is monitored by a high precision dial gauge that is tracking removal micron by micron. And then stub is reheated to safely melt the glue and release the pre-thinned sample. So precise alignment between the grinded disc and the specimen stage is critical. So while an offset dimple can technically still be used in an iron miller, it drastically reduces the optimal thinning geometry and complicates final preparation. So you can see here two dimples. One is sitting at the center of the disc, and another is off center. The final frontier is an iron milling and ultramicrotomy. Iron milling is for metals and ceramics. So requirement is that before coming to iron milling, the samples must be pre-thinned to less than 30 to 40 microns. And iron milling is done by dual argon ion beam bombardment in a strict vacuum chamber. For polymeric sections, you need bulk sample machined or small samples in a cone-shaped dressing, and it directly cuts the sample through glass or diamond knife, and it is done in ambient with attached water boat. So you can see here an iron miller. So it's a very delicate and highly expensive vacuum system designed to erode material at atomic level. Uh, So it has a specialized locking lever and clip system that secures a fragile 3 mm disc, and then the airlock control allows a duo post to be safely lowered into the vacuum chamber for milling and raised for venting. Then you have a stereoscope viewport which allows real-time visual monitoring of the milling action once the shutter opens. Then below you have the controls to control the RPM of rotation, the beam energy, and operation duration, which can range from 30 minutes to half a day. So the iron beam miller utilizes top and bottom guns to bombard both surfaces of the specimen simultaneously until a microscopic perforation appears at the center. So it is, if we use a steep angle, it will create a very narrow thin region we can't, which we won't be able to use in TM. So we use a shallow angle which produces a wide, highly usable electron transparent region. So for polymers, mechanical pre-thinning is bypassed and the specimen is mounted in a cone-shaped resin block and then cut directly using highly synchronized automated movements. So you have this machine where you can control your specimen holder arm, and you can look through your stereo microscope, and you can control the stage. So the speed you have to control. So you control velocity of the specimen arm moving against the knife, which is measured in millimeters per second, and the speed is the physical step size of the material advancing forward, which is measured in nanometers. So example setup of 1 millimeter per second speed paired with a 100 nanometer step size jump yields perfect 100 nanometer thick sections. So the plunge is a cone-shaped polymer resin which advances at a programmed feed rate, sharing exactly 100 nanometer of material against the edge. Then you have a float. So because the section is invisible to the naked eye, it floats seamlessly onto the surface tension of the attached water board, and extraction is done guided by the stereo microscope. The operator uses a tweezer to carefully fish out the floating section from beneath using a copper temp grid. The extreme sharpness required for microtomy means the cutting edge degrades rapidly. Rather than buying pre-made blades, researchers use a knife maker to produce fresh glass knives on demand. So this is a knife maker, so which is used. You take a standard glass strip, secure it using clamp, then you scratch and load. A perfect sharp scratch is made onto the surface before applying physical load to snap the glass cleanly into squares, and the square is then broken diagonally, producing two perfect sharp triangular knives ready to hold a water boat. So the complete ecosystem as a glance. So you have bulk material. So for ceramics, you will do ultrasonic cutter, then dimple grinder, then iron miller. For metals, you will use disk sponge, then dimple grinder, iron miller, and finally plasma cleaning. For polymers, you will do first resin mounting, then ultra microtome, then chemical staining for contrast. So you can see here the camera equation dictates that the physical distance r of any diffracted beam onto the screen is inversely proportional to the atomic plane spacing, and the product wavelength and camera length lambda L is acts as a universal constant. So you have to decide if the pattern is isolated, organized as isolated dots. If it then it is a single crystal, or if it is organized as concentric circles, then it is polycrystalline. For single crystal, we use zone axis guessing. For polycrystalline, we use R ratio tabulation. So first is the visual symmetry check. So before attempting mathematical indexing, we have to verify if the unknown pattern matches a highly symmetric low order zone axis. If it lacks these symmetries, then rigorous guessing is required. So if if the zone axis is 100, then it will have a square shape and the ratio would be 1:1 because it's a square. If it is having a 110 zone axis, then the shape will be rectangle and the ratio would be 1 by square root 2 for BCC or simple cubic. And if it is 111 zone axis, then shape would be hexagonal or equilateral and it will have 6-foot symmetry. So zone axis guessing algorithm, first step is guess a low order axis. So first you exclude failed symmetries, like symmetries which cannot happen using selection rules, like for FCC HKL must be unmixed, so mixed values will be removed and unmixed will be used, and for that we use the lowest for next lowest index. Then we apply the Weiss zone law and we calculate the dot product of the guessed axis and low order plane normals, and result must be exactly zero. So we studied that HU plus KV plus LW equals to 0. So we have to apply that formula here to see if that is applying. After that, we apply the camera equation ratio, that is R equals to lambda L by A into square root of h, h square plus k square plus L square, and do the calculated theoretical distances match the physical screen measurements. So if they match, then we have got the reciprocal lattice and we can expand further. If it doesn't match, we come back to step 1 with the next guess and then continue checking. So we read that the zone axes are perpendicular to the lattice planes. So zone axis dot lattice plane should be equal to 0. That is why we get HU plus L KP plus LW equals 0. So we first guess against low index planes. Like we assume our zone axis is 210. Then we guess against low index planes like 111. We do not get 0. 002 we get 0. 24 dash 0 we get 0. 133 is again not 0. So we get the 002 and 240 are appear promising as due to perpendicularity. Then we do the distance ratio test. So our target screen data is horizontal 1.1 centimeter and vertical 0.65 centimeters. So if we do 210, we get, and reference plane is 002, we get 1.45 centimeters. So which matches our value of 1.10. So this means that 210 zone axis invalid. So next we guess 211 and we take the reference planes and we get the result 1.06 centimeter, which is closely matching the target 1.1 centimeters. So we get that this is a 211 zone axis. And from there we can expand the reciprocal lattice. So by assigning indices to two valid fundamental planes, the entire diffraction net is indexed via linear combination, that is vector addition. So we can do vector A plus vector B. So incremental rules for this net: along rows delta H is 0, delta K is plus 2, delta L is minus 2. And along columns delta H is minus 1, delta K is plus 1, delta L is plus 1. So that is for this particular zone axis. That is for this particular lattice symmetry. So next we have polycrystalline rings. So we take the radius of each ring and we calculate our d. So we get r. So we substitute d as a by r square root h square plus k square plus n square, which gives us the formula r square equals to lambda l by h square, h square plus k square plus n square, and we define this as n. So we get that all r square values are strictly proportional to the integer sequence n. So no n value can exist for the formula 8n minus 1. Therefore, integers n7 and n15 are permanently forbidden and missing from all ring patterns. So we can see here for simple cubic, we get high density of evenly spaced concentric rings because it will allow n sequences 1, 2, 3, 4, 5, 6, 8. So the diagnostic rule will be all n values will be present except the forbidden values such as 7. Then for body centered cubic, we will have ring space predictably with r square changing in steady step. So the allowed n sequence will be 2, 4, 6, 8, 10, 12. So the diagnostic rule will be that only even numbers will be there. Then for FCC, we'll have distinctively repeating patterns. There will be two closely spaced rings, then there will be a gap, then again there will be a ring because the allowed n sequences are 3, 4, 8, 11, 12. So it will have mixed sequences. So we index unknown rings using ratio tabulation. So we measure all the different radiuses. Then we take the ratio. So we see if we have simple cubic, the ratio should yield square root 1, square root 2, square root 3, square root 4 values. If it is BCC, it should just square root 2, square root 4, square root 6, square root 8 values. If it is FCC, then it should give square root 3, square root 4, square root 8, square root 11 values. So you have to measure carefully because early values carry higher human error because the radius is small, so there can be error in measurement. So tabulating ratios against smaller inner radiuses normalizes physical data, which reveals the underlying theoretical end sequence and identifying the crystal structure. Then this can also be then used for finding the camera constant by calibrating against a known standard such as nickel. So the slope of root n versus r yields an exact camera constant, allowing calculation of interplanar spacing for entirely unknown materials under identical microscope conditions. So we take a known standard such as nickel, we for which all the ring radiuses should be known. We plotted we plotted we should get a straight line with and the slope of that slope should be equal to a divided by lambda l. So since a is known, we can easily get the value for lambda l, and then the same lambda l value then we can use further for different samples. So for both the vector analysis and scalar analysis, we use the equation RD equals to lambda L. So vector analysis requires finding 3D directionality, which is resolved via zone axis guessing, mapping perpendicular planes via dot products, and vector addition. Then for polycrystalline, we use scalar analysis because we eliminate directionality, and it relies entirely on magnitude of radius measurements and scalar properties and theoretical integer sequences. Then we come to practice questions. Which among the following is a beam sensitive material? Metals, composites, polymers, ceramics. You can write your answers in the chat. So that is correct. The answer to this would be polymers. So polymers are sensitive to ion beam. They will get burnt out. Hence, we don't use ion beam milling for polymers. The diaphragm or aperture discs are made up of dash aluminium, platinum, titanium. So that is so that would be platinum. So so the purpose of aperture disc is to allow only a allow only a portion of the beam to pass through, which is going through the center hole, and block and absorb the other beams that is falling on the disc. So for that we need a high density material. We need high density materials such as platinum. Aluminium and titanium are both low density materials, so they won't work. They will not absorb the electron beam that efficiently. To record the microstructural images, both objective and SAD aperture are required. True or false? So it will be false. So to see the microstructural images, we only need the objective apertures. SAD apertures are required when we want to do selective rate diffraction. Dash method can be used for the preparation of polymeric or soft TM samples, jet polishing, ion milling, ultramicrotomy. So the answer to this is C, ultramicrotomy. So jet polishing is not used for metals, metallic polishing, metallic thinning. Iron milling is used for both metals and non-metals. Uh, Ultramicrotomy is the one that is used for polymeric and soft samples. When using ultramicrotome for sectioning, what is the purpose for using glass knife? To trim the cutting edge of sample blocks so as to make it flat, to section the specimen into thin slices, to hold the sample blocks, to allow us to monitor the process of sectioning. So correct answer here is to section the specimen into thin slices. Which of the following is a pre-thinning technique and not final thinning during team sample preparation? Iron milling, jet polishing, dimpling, ultramicrotomy. So the answer to this would be C, dimpling. So dimpling is a pre-thinning technique and all other three are final thinning techniques. The camera constant is given by RD, L lambda, LRD. The answer will be L lambda. The diffraction pattern is formed on back focal planes of objective lens, image plane of objective lens, specimen plane, front focal plane of condenser lens. So the answer to this would be back focal plane of objective lens. So specimen plane is where your sample is kept. Front focal plane of condenser lens is where your condenser aperture is kept. Image plane of objective lens is where your images are formed, and the diffraction pattern is formed on the back focal plane of objective lens. Which aperture is used to form the selected area diffraction pattern in TM? Objective aperture, SAD aperture, condenser aperture. So the answer to this would be SAD aperture. So again, the condenser aperture is used to shape the beam by changing to change the spot size. Objective aperture is used to used for imaging and for SAD selected area diffraction. We use SAD aperture. The arrangement of apertures vertically from top to bottom are objective aperture, condenser aperture, SAD aperture, SAD aperture, condenser aperture, objective aperture, condenser aperture, objective aperture, SAD aperture, SAD aperture, objective aperture, and condenser aperture. And the answer would be C. So if on the top we have condenser aperture just below the condenser lens, then you have objective aperture below the in front of your and below your specimen plane, and below the objective aperture you have your SAD aperture, which you can then, and they are movable, so you can move objective and SAD aperture in and out depending on which measure, which what you want to do, of imaging or diffraction. The principle of thinning in jet polishing is chemical attack, anodic dissolution, twin jet pressure, mechanical thinning. So the correct answer to this would be A, chemical attack. So in jet polishing, what we are throwing on a metal disc is a electrolyte which is chemically reacting with your metal and thinning it down. So it is a chemical attack. So that is all I had for today. So If you have any doubts, you can ask. Also, there would be an extra session on Tuesday, same time, so you can ask your doubts then also. So, if you want, you can attend the Tuesday session 6 p.m. to 8 p.m. Same Google Meet link. Uh, Thank you for attending these sessions throughout the course. So, as we as has been told earlier, also the exam would be pen and paper, and it will contain all types of questions, MCQs, fill in the blanks, short answer type, long answer type questions. I do not have the exact pattern with me. So this is an NPTEL thing. You have to ask the NPTEL help help desk for this.